Okay, so just a few announcements before we get going. Today's the last day of COVID watch on our first couple of exposures. I'm taking my mask off because these things are blowing real hard and I want you to be able to hear me and I'm trying to yell over these things. Thanks again to the students who told me directly that they were ill. I suspect many of you are watching over Zoom. Thank you. Or over, not over Zoom, but over the recordings on YouTube. And please remember to report to the university. I don't think I have any new exposures that I know of that we're going to hear about pretty soon. So we seem to have gotten through this. I have heard anecdotally that contact tracing on campus says that they are as busy as they were at the height of January's peak right now. So while chemical engineering seems to have been spared, it does seem like it is rampantly running around the university in general. So just keep that in mind, like student union and that kind of thing. So today we're going to finish our discussion of energy. We're going to start discussing Bernoulli. I was looking at my notes and reviewing lectures from last year, and I realized on Wednesday we kind of have a choice, and so I wanted to put it up to you all right now. We can do so. I had originally slated that we were going to do examples on the board on Wednesday. But I've actually made YouTube videos of all the examples that I had slated for us to look at on Wednesday. So I can replace them with new examples if you want. We also have to get through chapter 4 before the midterm exam. And last year that got a little bit bunchy, as in the midterm review lecture. I had some new material to go over that lecture as well. Kind of giving it to you as a choice. On Wednesday, we can look at some examples on the board, or we can move on to chapter 4, which should give us plenty of time for midterm review before the exam. My preference is number 2. I am going to put my hand on the scale here. This is definitely my preference. But I did want to let you all have a say here. And Michael, Jeff.
Would the examples be on Bernoulli's equation specifically, or
examples would be on chapter 3 in general. So the idea of kind of examples, we run through examples on slides, right? But the idea would be 2 examples on the board on Wednesday. I will also upload some new examples on YouTube, right? As we go. So it's not like we not get any more examples about chapter 3 stuff if we choose. Yeah.
would the examples be significantly different from like what's in your homework? Or
No, the examples would likely be more problems that I run through in class. Not from your homework, but other problems in the back of those. And again, my plan is to make more of those go on YouTube, regardless of what we do. Any other questions on kind of around? Yeah. You will have, I will give you all the exams as examples. You've also been getting practice on exam problems on your homeworks. I don't yet have enough material back catalog to give you entirely correct practice exams prior to the exam. Right, so I'm giving you pieces of the 2 exams from an exam from the 2 times I previously taught the course. But I will give you the entire exam, including bits and pieces you've seen on homework. Entire previous exams of the course. Any other questions? All right, so just by show of hands of who's here. Examples on the board. Who says number 1, examples on the board on Wednesday? Who says number 2? Okay, all right, so we're definitely moving on to chapter 4. Okay, I figured if it was close, we were going to have to do a web form or something to include everyone, but it's pretty overwhelming. So does it seem like examples on the board don't work for you all, or why? Okay. Yeah. Okay. Great. Okay. Because I do occasionally want to do this, but I just thought it would get a little bit fancy. All right. So we're going to move on to chapter 4 on Wednesday. So chapter 4 is going to be differential equations of fluid motion. And today we're going to be finishing up energy and Bernoulli. Any questions on course material or anything else before we get started? Okay. All right. So now we're on to work. So remember, we said we had written out an energy balance, a form of the energy balance from the Reynolds transport theorem, which is a balance for the rate of change of energy within the fluid. And we said that right? So we had dE dt is the rate of change within the control volume plus outflows minus inflows. And right now we're still looking at the things that make up this dE dt term, right? And we said that it can be the energy in the fluid can be changed by heat or by work. We started actually defining some of the things that can do work, and we're going to go into those in a little more detail right now. And remember, by convention, positive Q is heat added to the system. A positive W is work done by the system. And so we said dE dt, dQ dt minus dW dt. So we're going to start looking at work right now. We'll say this work term. So we're going to typically write it out as W dot, right, instead of carrying around those DDTs. We're going to say it's the shaft work plus pressure work plus the viscous work. And we'll often abbreviate those as WS plus WP plus WB. Right. So shaft work is anything that's has some kind of like a spinning shaft in the fluid. Right. So this could be a turbine that we're using to extract the energy from the fluid. It could be a pump where we're actually putting energy into the fluid. Right. In which case the sign is going to be the opposite of what we had. We'll get pressure. This is work done by pressure. We'll develop what this, or we'll see what this looks like. And viscous, this is like viscous drag. Friction within the fluid is another way of extracting energy from it. I have put in a work order on the AC, but we're still waiting on that. So the first of these, shaft work, is work done by the fluid on a machine inside the control volume. Right. Remember that. I'm just going to go back again. I should have this on this slide. But positive W is work done by the system, work done by the fluid. Apologies for skipping around. So shaft work is work done by the fluid on a machine inside the control volume. So for example, this is a centrifugal pump that has an impeller. This comes from your book in chapter 11. And we would define all of the interactions of the fluid with this centrifugal pump as being included in the shaft work term. In this case, this is doing work on the fluid. So there's much more on mechanisms of how to like exactly what's going on inside of pumps and turbines, this kind of thing in chapter 11. It's about turbo machines. We are not covering this extensively in this class. We'll talk a little bit about pumps when we discuss pipe flow. But for the most part, we're just going to account for the amount of energy that is put into the fluid or taken out of the fluid by turbo machines or by pumps and impellers, this kind of thing, using the energy balance. Okay. But this shaft work turn, if you look in here inside of this pump, we'll see that there are all kinds of different interactions going on, right? There's, for example, viscous drag by the fluid interacting with the pump casing and with the with the impeller itself. All of those things, all of those the viscous drag and everything that's going on within this pump is going to get lumped in with the net work that's being done by this pump. So when we say W dot shaft, we're saying the net amount of work done by the fluid on a machine inside the control volume. Right, so accounting for all the interactions with that piece of equipment. We're kind of ignoring the details of like what exactly these does its flow look like. We're kind of ignoring that. We're just saying what is the amount of energy, what is the rate of energy change due to that piece of equipment. Makes sense? So for the second term here is the pressure work term. And the way to understand where this comes from, I really just want you to understand where this comes from. So if you remember back to like a physics 1 type thing, work is force times velocity, right? That holds here as well. But if we had a cart that I'm moving along the floor of the lecture hall, or I take my water bottle again and I slide it along this deck, right? There's a frictional force that I'm opposing, right, as I'm pushing it here. And if I push at a constant velocity, I am doing work against that force. And the amount of work that I'm doing is the force that I'm applying times the velocity with which it's moving, right? That's the work. Same thing holds for a fluid. And this is how pressure exerts, can do work on a fluid. And so we can say that the rate of work on a differential fluid element, so if I have some little differential fluid element here, is the pressure force minus PdA. So pressure is a force per area. So it's that pressure force times that area, negative sign for exerted input. Times the velocity as it's moving into the control volume. Right, so a force times the velocity is how we find the work. Your book goes into a little bit more detail on this, but what we end up with is that the total pressure work is the integral. We can write out as this integral here. W dot P is the integral over a control surface of P times V dot N dA. Okay. Where I've lost, there's another negative sign. Ready to notice there's a negative sign discrepancy here. That's because this N is the outward facing normal. And what we needed to consider here was the velocity going inwards. So it's in the opposite direction of that normal. So that's why this ends up positive. This term ends up positive. So the total pressure work is the integral of the pressure times the component of the velocity normal to the surface integrated over the area. Okay. So right now, what we're doing basically is just accumulating terms that are going into that dE dt. We covered shaft work. We said it's just going to be basically the net amount of energy produced by some kind of turbo machinery. This is what we're going to plug in for that pressure work term, and what we're left with is the viscous work term. The viscous work, W dot V, is due to viscous stressing acting on control surface. Finding it hard to illustrate these things, so I tried to turn it into these AI tools. This is what you get for fluid stress work. So I thought it was kind of nice. I expect it to be something a lot more stressful. But for so viscous stresses, sorry, again, are basically friction within the fluid, and that can extract energy from the fluid itself. Just a few notes about this term. Your textbook spends more time talking about where this term is neglected than where this term is important. This term, but basically in the common forms of the energy balance, we're going to often neglect this term. So for example, at a solid surface, the velocity goes to 0 based on the no slip condition. So if we have a solid surface that's not moving, right? The velocity is equal to 0. So actually, at any solid surface, the velocity of the fluid is equal to the velocity of the solid surface, meaning that at the surface itself, the fluid, there will be no net amount of work being done by the viscous stresses on the surface. Again, work would be like the force times velocity. And since the velocity of the surface is equal to the velocity of the surface, so the relative velocity is 0. There's no work being done by viscous stresses at the solid surface itself. So at the solid surface, V is equal to 0. At the surface of a machine, as we mentioned, the drag, any viscous drag effects are going to be included in that shaft work term. We're not going to. So if we have, some kind of a turbine or something that we're spinning with a fluid, we're not going to say that we have a shaft work term plus the viscous work that's that's being done within that piece of equipment. We're just going to say that all of that is lumped into the net shaft work term. So we're going to ignore the viscous work term there. If we have an inlet or outlet normal to the flow, so again, this is another reason to choose your control surfaces normal to the flow. Then the normal components of the viscous stress are typically negligible, and so we're not going to have any viscous work being done at inlets or outlets that are normal to the flow. So basically, the only time that this term is important is if our control volume boundaries are on streamlines within the fluid. So what I mean is that if we take, if this represents some flow within a fluid, and we were to draw boundaries, our control volume boundaries were within the fluid, entirely contained within the fluid, and following along with the flow. Right, so not at a solid surface, not normal to an inlet or outlet, following along with the flow, then we often are going to have to include these viscous stress terms. But most of the time, if we draw our control volume correctly, we can ignore them, and we're going to assume for now they're not important in most cases. So we will be lumping this into a viscous work term, and we're going to discuss how to calculate this later. So, for example, when we discuss pipe flow, we're going to have to include viscous work. We're going to have to include friction work. But for the most part, in our chapter 3 type problems, we're going to be generally ignoring this term, okay? Until we learn how to calculate it in our chapter on internal flows. All right, so if we put this all together, we're going to say that dE dt, right, E dot within the fluid is Q dot minus W dot. It's going to be comprised of those terms that we just discussed. We're going to plug in a second. Remember, this is equal to, based on Reynolds transport theorem, the rate of change within rate of change of energy within the control volume, plus the flux through the control surfaces, which we can write out this way in terms of the unit normal, that N, right? So B dot N. So the flux across control. And we have for the work term, we have shaft work plus, this is what the pressure work turned into, plus the viscous work. So a lot of times in chapter 3 we're going to be ignoring, but it's going to be important when we start talking about pipe flow. And now if we plug this in, actually before we plug this in, so I'm going to take you back one step here. Before we plug this in, I want you to notice that this looks a lot like the flux through control surface term, right? What's going on inside this integral here is very similar to what's going on inside that integral up above. So, so what we're going to do is we're going to take this term. That's why this is the only one of the 3 terms that we actually wrote out explicitly. So we're going to take this term and we're going to lump it in with the energy of the fluid that is moving through those control surfaces, right? Because those integrals look so similar, it's convenient to lump those things together. And so when we do that, we end up with this form of the expression, where we have Q dot minus WX minus WB, right? So the heat, heat flux minus the shaft work minus the viscous work, the rate of change of energy within the control volume, plus this integral over the control surface now of E, energy per unit mass, plus P over rho times rho times the T dot N TA. Okay. So we've lumped the pressure term in again with that energy of the fluid term. Okay. And now we're going to expand that E term, right? Remember, we talked about energy in a fluid. We said that there's internal energy, kinetic energy, and gravitational potential energy are the 3 terms we're going to consider. And now if we remember thermo, we can write out enthalpy as our internal energy plus, in this case, the P over rho. And so now we can take the internal energy part of little e combined with this P over rho and just have our enthalpy. Right, so that's why we did that work on pressure work to get to this term. And so now our full form here, right, is the heat minus the shaft work minus the viscous work. There's a rate of change of energy in the fluid through the control volume. Remember, this is internal energy. Kinetic energy, gravitational potential energy. Plus the integral over our control surfaces of the enthalpy plus kinetic energy plus potential energy that's being affected through those control surfaces. Okay. All right, any questions on this? So next step is we're going to start simplifying into forms that'll be more convenient if you can use them. Yeah.
If you just go through once again and explain the velocity.
Yeah, sure. Okay. CV, this is control volume. V, this is velocity. Remember, this is the kinetic energy term, right, of the energy within the fluid. So the V is velocity. D third V, this is volume. Okay. And the reason I'm using this is so I'm not using the same letter. What's this V? Velocity. What's this V? Velocity. Okay. Any other questions? Yes. Yeah. So yeah, why the hats on U and H? We normally use those for unit vectors, but these are not vectors, right? And these are scalar quantities. The reason is we're going to start writing things out in terms of heights that we're going to use the letter H for. Without a hat. And so as to not get into Greek letters and to not confuse this with heights, we're going to be at this hat here. That's primarily because it's not a thermo book, so we're using this for stuff. Okay. I saw another question back. Yeah. Yeah, no, it'd be great if we could start making up letters. I mean, we can start going deeper. We haven't gone that deep into the Greek alphabet, so we can start doing some deep cuts and writing out C and all kinds of other things if you want. Yeah. I'm gonna start. Yeah, so we're gonna have like the blue H is this and the red H. Now, I agree. It does get a little bit confusing. I'm trying to mitigate that with font choices. And I'm mostly following the convention of your textbook here, right? So your textbook uses some script V or something for volume. This is how it renders in my Monday. And your textbook uses this convention, so that's what we're calling it. All right, any other questions? If you have suggestions for new letters, just let me know.
Again, we should Cyrillic alphabet.
We can use Cyrillic.
33 more letters.
Yeah, sure.
Oh, it's the Asian characters. It's hundreds.
So first, we're gonna have something on penmanship. That's gonna be the first unit. Is how to write out all these letters. And then we'll get into it. Okay. So now we're gonna start. So again, our common playbook here, right? We start with Reynolds transport theorem. We derive a general form or write out a general form of our balance equation, which is what we have here. Then next, now we're going to look at simplifications, right? So the first of these is going to be for uniform or 1D inlets and outlets. So if our inlets and outlets are one-dimensional, meaning the velocity is uniform across the inlet or outlet, then this integral across the control surface simplifies pretty greatly. We have the sum across our outflows of energy plus that pressure term within the fluid times m dot minus the sum through our inlet control surfaces of the energy within the fluid, again plus that pressure term contained in the enthalpy times m dot. So this whole thing vastly simplifies if we have uniform velocity across our control surfaces. The next assumption that we typically apply, right, and this is exactly analogous to what we saw in momentum and mass, right? This is the easy case for us to consider for inlets and outlets across control surfaces. I say easy because now there's many more things to keep track of, right? When we're talking about energy, than there were in momentum or certainly in mass. But at least it's simpler than this form. And now we're going to see what happens when we look at steady one-dimensional flow, right? So now if we have steady state, what does steady state imply? No change in time, dt equal to 0, right? So that's that first term on the right-hand side will typically disappear. So for steady flow, let's look at steady flow, one inlet, one outlet. So I have some control volume here with some inlet, which I'm going to call control surface 1, some outlet I call control surface 2. Meaning m dot 1 is m dot 2 is m dot. So in this case, now my expression, my Reynolds transport theorem boils down to this, right? So I have my heat, my work terms, my shaft work and viscous work terms, and then these are my ddt term is dropped out because I'm assuming it's steady. And since it's one-dimensional, I can rewrite my inlet and outlets this way. And now, yes.
So just for, is it also 1D and steady state? Right.
So steady state needs that ddt term, right? The integral over the control volume with the weird v that everyone hates has gone away, right? Yeah. One-dimensional means that my control surface integral with the v dot n that everybody hates turned into this. Okay. So
one-dimensional means one inlet and outlet.
Sorry, one-dimensional means uniform. Yeah, so that's why I try to write this out as uniform, and I suppose I did here. So one-dimensional in your textbook means uniform velocity across the inlet and outlet, meaning so you see I'm saying that the velocity is the same going all the way across that face. Okay. So there's no velocity profile. Yeah, right.
Is that only true for one in and one out? Or
That's not only true for one in, one out. So if you remember sometime ago, we looked at an example, or last class, we looked at an example where we had some big control volume, and we had, I think, one outlet and two inlets. And we looked at energy conservation within this control volume, and we found that dEdt was this big negative number. And we tried to decide where we talked about where those things come from. In this case, we also assumed uniform. And that really just means that the velocity across these control surfaces was constant, or we were assuming it's basically constant.
they're not equal to each other.
It's just constant. Yeah, not necessarily. Yes. Yeah. In fact, in this case, yeah, even with one inlet, one outlet, they don't have to be equal to each other, right? If they're different areas, by mass conservation, they have to be different velocities, right? So yeah, so they don't have to be equal to each other, just constant across the control surface. And the counter example to this, maybe for help, is if we are considering flow within a pipe, which we will at some points. Considering laminar flow within a pipe, we're going to see that we have ended up with a parabolic velocity profile. And with the parabolic velocity profile, this is non-uniform, right? Because the velocity is not constant across this surface, right? So this is what we mean by non-1D, non-uniform. Okay, in this case, we should be. So we are going to take all of our work and heat terms, and we're going to express these terms now per unit mass. And if we rearrange these terms per unit mass, we write these terms per unit mass and rearrange, we'll end up with this expression here. Basically, it's telling us that balance for our inflows minus everything that's coming out of the fluid. Inflows minus outflows. So we have our energy flowing in, is energy flowing out, minus the heat transfer to the fluid per unit mass, plus the work we take out from the fluid. Yes.
Why is the work now small?
So the work is now small because we're taking it per unit mass, right? So like when we had big heat, right? And we said, in Reynolds transport theorem, now we said now with P, and we said, energy per unit mass with Lilly, we've done the same, we call the same thing. Okay. So energy flowing in is equal to energy flowing out minus heat transferred to the fluid per unit mass plus the work done by the fluid. And so, with one inlet, one outlet, we get this much simplified form. We can make other simplifications, though, to this energy balance. So if we assume it's low speed, therefore, that implies in a fluid, that implies that it is incompressible and therefore constant internal energy. And so if we have constant internal energy, right, the U term, those U terms, basically inlet and outlet are going to drop out, right? We have constant internal energy within the fluid. And so now our enthalpy, right? Remember our enthalpy was that internal energy plus P over rho. Our enthalpy, if we have the same U in and out, then those drop out, and we're just left with the pressures in and out. Now our enthalpy term resolves to P over rho on either side. So for incompressible fluid, we now have P over rho plus the kinetic energy per unit mass plus the gravitational potential energy in is equal to the same terms out, again, minus heat plus the work. Yes.
So low speed then would be relative to the fluid.
Yeah, so low speed here is relative to Mach, relative to Mach 1, relative to the speed of sound, right? So low speed means that the fluid is traveling substantially less than the speed of sound. Yeah. Mach number is much less. Good question. So remember, like, for water, we treat water typically as incompressible, right? Most liquids we treat as incompressible, and gases at low speeds we also treat as incompressible, right? So the air that's rushing out of this inlet vent and making it hard for everyone to hear everything, even though it sounds like it's rushing pretty fast, it's actually low speed relative to the speed of sound. And if we were analyzing this HVAC system, we treat this as incompressible. So we're going to put this form of the expression. So next, we're going to simplify our heat and work terms. We're going to say that any work done at pipe walls, we're going to call friction. So we're going to include some friction. We're going to take that viscous term, and we're just going to say that, let's just say there's some friction in the system. And we don't yet know how to deal with that, but we will learn how to deal with that in the pipe flow unit. And we're going to ignore anything else that might cause viscous work within the fluid. So we're just going to have friction. Yeah. Yeah. We're going to see that when we get to chapter 6. So we're going to derive this term. What this term exactly how to compute this term in chapter 6. We consider velocity. Okay. Is that okay? Yeah. Okay. To leave it as TBD? Well, because we have a few more tools to develop before we really understand what's going on there. Sorry. Suspense, though, when you're trying to learn things, doesn't always work. So I'm aware of that. But we are going to spend a significant amount of time talking about where that comes from. We're going to ignore other viscous work. And now we're going to split that shaft work term into a turbine work, which is positive for work done by the fluid, and another sign convention change here, minus work done by pumps, which we're going to define as positive into the fluid. Okay, so say W shaft with W turbine, positive for work done by the fluid, minus W pump for positive for work done on the fluid. And now we're going to end up with this expression here. So again, inflows equal to outflows minus Q plus that new WF friction term minus W pump plus W turbine. Apologies for another sign change, convention change, but this is now in a form that if we look at these terms here on the right hand side, So the form that should make it a little bit easier to avoid sign errors as you're working these problems, because when we're talking about a pump is adding energy to the system. And so now if we have, you know, a 10 horsepower pump or something, then we can write that as like a positive 10 horsepower. And then subtract it on this side. And if we have a turbine extracting a certain amount of energy, then we can just write that term in here. Okay. I'm writing a boxer on this because this is an important term, an important equation for us to remember for solving problems, right? We said in general, until we get to chapter 9, we're going to be considering incompressible fluids, right? We're often going to be dealing with one inlet, one outlet, and steady state when we're trying to solve energy balance problems. So this is an important one to keep in mind. Yeah.
For units like work, unit energy load. Is it safe to put a bar under it for us, or is that going to be something else later on?
Sorry, unit. Sorry.
You know, we do the underbar sometimes for like work, it could be a mass. Is that going to be something for something else? Fluids?
No, I don't. We're not going to be using an underbar. We don't use an underbar for anything else. In fact, I don't think that comes up in your textbook. That I'm aware. Cool. Okay, so one note on one-dimensional inlets or outlets. One-dimensional or uniform inlets or outlets. So this form of the equation is really convenient to use, right? Because the we've gotten rid of that integral over the control surface, right? And that whole v dot n thing went away when we assumed uniform inlets or outlets. And so it would be nice if we could figure out a way to use a similar form of this expression for non-uniform inlets or outlets. This is where we get the kinetic energy correction factor. So if the inlets or outlets are not uniform, it's really just the kinetic energy term where we have this like v squared multiplying a v, and where our integral becomes something more complex. And so we just define this kinetic energy term integrated over the control surface as alpha times 1/2 v squared average times m dot. We can actually then solve for what this alpha term is. And so v av is the average velocity across the control surface. Right, so if I come over here to if I have velocity through I have flow through a pipe, laminar flow through a pipe, and I have some parabolic velocity. Redrawing it a little bit bigger. I have my average velocity is something like this. So I can rewrite, so if I can solve for what alpha is, then I can rewrite that kinetic energy term in terms of just its average velocity, get something that's analogous to that uniform inlet system. And so we can solve for alpha this way, 1/a integral of u over v average cubed dA. Is that u velocity? U is velocity. U is the component of the velocity. Yeah, u is the component of the velocity that is normal to the surface. What's that? It's the integral over the surface, over the area. Yeah. Yeah, so u is what we normally use as the x component of velocity. Lowercase u. Lowercase v is what we use as the y component of velocity often, although I've skipped doing that so far. That's going to come up in chapter 4, though. So for laminar flow, in the case where we have a parabolic velocity profile, alpha is 2. So we actually have a pretty significant correction factor here. In turbulent flow, alpha is pretty low. It's pretty close to 1, and we're generally going to ignore it. We're going to talk a lot more about turbulent flow when we talk about flow in pipes. But with this kinetic energy correction factor, we end up with this modified version of the expression with just an alpha in front of the kinetic energy terms. Okay. So same basic expression, but now we just have these alphas. Okay. Okay. So some notes on energy balance, and this is why we have that H hat. We sometimes will write this in terms of a head, which has dimensions of length. It's equivalent to the elevation of a fluid column at a given pressure. So it's like your fluid statics type thing, like a way of measuring pressures. So in this case, we're typically going to be, we're writing out things in terms of this head. We're typically ignoring heat transfer. It's awkward to talk about a heat transfer in terms of these units of head. And so in that case, the form of our expression becomes this, where H is head, not enthalpy. So that's why we use that H hat, right? And so we have P over gamma, right? That's just rho G, V squared over 2G plus Z on the inlet. The same thing on the outlet, plus we say the head loss due to friction, the head gain due to the pump, and the head that we take out due to the turbine. We'll see when we're dealing with pipe flow networks, this can be a convenient way to talk about flow in pipes. This is how your textbook deals with flow in pipes, is in terms of heads through pipe flow networks. And so this is the convention that we're going to follow when we get to pipe flow. Just be aware, that's where we're going. That's what is the local pipe flow? So head is like, so if we have a given pressure, let's say we have a given, so in a fluid, we have a given pressure at the inlet, plus, let's say we just have a given pressure. There's no velocity and we're at c is equal to 0. The head is the height that a fluid column would rise to above wherever the fluid is, right? So that would be the height of the fluid column. And now if we start adding in a velocity, what we're basically saying is that that velocity carries energy, and that energy can also give rise, can also push the head of that fluid column up. And so it's a way of accounting for all of the energy within the fluid, just in terms of like an equivalent gravitational potential energy. Right. So basically, so another way of thinking about this is that we're casting all of the energy terms, inlets and outlets, in terms of heights. And it's basically allowing us to then keep track of the energy in the fluid, all the different forms of energy within the fluid, in terms of an equivalent gravitational potential energy. We'll also look at a video of how this plays out in pipe flow, I think maybe on Friday as well. Just as a preview for pipe flow and as an introduction to what energy head is. Yeah.
So the like your half B in the squiggly and the straight B, that's specific weight.
Sorry, it's gamma again. This is the specific weight, rho G.
And basically it's like the inlet height plus any H increase in like pumps minus friction in the turbine give you the pump, right?
That's right. Yeah. So if we had, so for example, if we have fluid starting at 0 velocity at some height, right? Then that would be the initial at some height above the floor, above a reference altitude. That would be, that fluid has gravitational potential energy. And it can now turn into kinetic energy, right? As the fluid flows down an incline or something. This allows, we're basically just keeping track of energy in terms of potential, gravitational potential.
So then we express all of the other work.
And now we're expressing all of these things in terms of this. That's why we're writing that.
So it's like the H of pump is how much height.
How much
energy is.
How much gravitational potential energy equivalent we're putting back into it would be that H of the pump. That's correct. H of the friction is how much of that gravitational potential energy we're losing due to frictional loss. Yes. So dimensions are length, units are feet, meters, inches, furlongs, whatever. Probably not, but probably feet or meters, miles, kilometers.
Furlong.
Favorite. Okay. Any other questions on this? Okay, and again, just a reminder, there's kinetic energy correction factor, just as with momentum. And in the head form of the equation, that just shows up as putting an alpha here instead of a 1 in the kinetic energy term. Okay. Okay. So now we have 5 minutes, less than 5 minutes left. And we're gonna derive Bernoulli equation. Serious. So we're gonna start from the one-dimensional incompressible steady-state energy balance. And we are going to say there's no heat, no work, no friction. So no heat, no work, no friction. And we end up with the Bernoulli equation. That's why we do it this way. Your textbook follows a different path. But so this is the Bernoulli relation for a fluid. Okay. We're going to write it out in a slightly different form. So let's see. So first of all, we can say that these two things, right? The inlet pressure plus this 1/2 P over rho plus 1/2 V squared for GC is equal to the outlet P over rho plus 1/2 V squared for GC. Meaning that's equal to a constant for the fluid, representing basically the amount of energy within the fluid. We'll often write this out as a delta of each of these terms. So you see this as P2 minus P1 over rho plus V2 squared minus Z1 squared over 2 plus G Z2 minus Z1 is equal to 0. But it's just that's just a rearrangement of this expression. You could also see this if we multiply through by rho, we would have 1/2 rho V squared plus rho GZ would be the same expression. But this is the Bernoulli equation. It is sometimes described as one of the most powerful equations or most useful equations in fluid mechanics. And when it is applicable, it definitely can be. So I want to return to the mantis shrimp example. So in the mantis shrimp example, or sorry, the pistol shrimp example, the narrator said, if you remember, that the claw, the force of the claw coming together, right, it creates this enormous pressure, enough to compress water appreciably, and that creates a jet of fluid that's so fast that we create cavitation, right? We actually boil the fluid off, and that creates a cavitation bubble. And when that bubble collapses, you get a popping, right? This tells us how that works. So it basically says that if we start from some inlet condition, let's say where velocity was initially 0, or velocity is initially 0, and the pressure is initially fairly high because we're underneath the water. And now we move to a condition where the velocity is enormous, right? The only way for these two things to be equal is if the pressure drops dramatically. So in general, as we accelerate a fluid, as long as we don't have other things going on, that's really important. But as we accelerate a fluid, the energy has to come from someplace. And if we're not moving up or down an incline, and C is not changing, then that comes from pressure, fluid pressure. So V goes up, T goes down. Right. So as that fluid is accelerating at really, really high velocity, the pressure decreases. And it decreases so much that we get below basically the point where the fluid starts to boil and creates these cavitation bubbles. So that's the type of thing Bernoulli equation is great for. It's getting some intuition into what's going on in fluid systems. But a note of caution, and this is where we will we're going to end on this discussion today, and we'll pick up with just a last note about Bernoulli on Wednesday before we get to chapter 4. It is incredibly widely overused, right? Because the simplicity of the Bernoulli equation is kind of seductive, right? You want to use it when you see a fluid mechanics problem. You know you have this tool that can be really powerful, and it is then often very, very widely overused. So we're going to talk a little bit more about restrictions on Bernoulli equation before we jump into chapter 4, and about how to use the Bernoulli equation responsibly. All right. Thank you all. I'll see you on Wednesday.